Hey everyone, welcome back. In today's video, we're going to continue the discussion of constraints. We're going to look specifically at gear and pulley constraints. We're going to do both of these together because honestly, they're very similar. So let's do the gear first. So here's the problem we're going to look at. We have a small gear and we have a big gear. And there's my drawing of the gear teeth that have been meshed together. In reality, gear teeth are going to look something like this. They're usually not perfect little triangles. They're going to have some design to them that looks like this. There we go. And what's going to happen is when one of these gears spin, this tooth, this gear tooth is going to dig into the teeth on the other one, and of course it's going to push it. Now, there are going to be forces involved in this motion. Those forces are not going to be perfectly perpendicular to this interface, but when you get to your classes in mechanical design, you will study in depth all about gears and how to design the gear teeth, what you need to make the gears out of. You particularly have to pay attention to this spot right here where one tooth digs into the next one. You have to make sure that it doesn't score or damage the other gear. And there's a whole depth of science behind the design of those parts. All right, so for the dynamics then, what do we want? We want the number of degrees of freedom. And remember, we talked about this in the previous problem. In order to answer this question about degrees of freedom, what do we have to do? We need to do position, we need to do orientation. From there, I'm going to ask that you list the generalized coordinates. After that, we're going to derive constraints. And of course, from there, if you have the number of generalized coordinates and the number of constraints, it's very simple to calculate the degrees of freedom. All right. So we want to do position and orientation first. Here's our diagram. What do we have to do? Well, we do the same thing we do for every other problem. We're going to start by putting an inertial reference frame on the problem. And we need an inertial reference point, some non-moving point. So just out of convenience, I'm going to put that point in the middle of the big disc, point in. Next, count the bodies. However many bodies you have, you need to be tracking some point on these bodies. So we have two bodies, the two gears. Let's say that the big gear on the right is body A, and I'm going to track point A, which in this case just happens to be the center of the disc. So it shares, right? It's the same point as point N, and that's okay. And we can put another point in the middle of this disc, and we can call that one point B. Now, what is a good point to keep track of these? Do we need to track the center of the disc? Maybe we could have tracked a point here on the outside of the disc. That's fine. Consider that this point on the outside of gear A, this point C, it's the same as any other point on the outside of this gear. This gear could be attached to something. It could be a part of some other mechanism, right? This could be some coupler, and the coupler is attached to a crank, and then the crank is connected to a motor. The motor generates a torque that turns the crank, it turns the coupler, and that drives the gear, which then drives some output gear, right? It could be a part of a larger mechanism, in which case, if it were, you definitely need to know where point C is, because that's going to be part of this mechanism with the rest of the chain. In this case, though, we're only concerned about finding the constraint for the gear. So I'm going to take this out, and in fact, we do not need this point C out on the edge. So in this case, tracking the centers, it's totally fine. The only thing that's really going to happen here, we know, is that the gears are going to spin. So we do need to put some frames on this, And I'm going to draw the frames like this because any direction, honestly, is equivalent on this thing. It's just going to spin. So there's XB and YB. Okay, position and orientation. The position vector from N to A. Well, they're right on top of each other. So P into A is 0. And again, it's perfectly acceptable to put these 2 points incident, to put them on top of each other, because this point in the center of the gear does not move. So even though I have point N attached to a body, right, that point is not going to move. So that's totally acceptable. Now, P in to B. We know that gear B is not going to move. So really, what is the point of this position vector? You're the engineer. You're going to build this thing. You need to know where these parts are going. So let's say that there's some vertical offset, there's some horizontal offset. We call the horizontal L1, we call the vertical L2. Now, what I'm gonna do, since the L1 and the L2 are fixed distances and they do not change, I am going to put negatives on this. So let's say to get from N to B, we have to go down and we have to go left. Both of those are opposed to the inertial reference frame. So this is negative L1 xn and negative L2 yn. These are not variables, right? These aren't q's. These are never going to take on positive and negative values depending on its motion. These are just fixed, and they're always in that negative direction. So that's what I'm going to do. So this takes care of the position of these things. What's going to happen with orientation? Well, they both have their own attached frames, A frame and B frame. Both of those frames are going to rotate. Consider, though, that they're not going to rotate at the same rate. If that doesn't make intuitive sense to you, think about this. If I spin this little gear and I spin it very quickly, it's going to make the big gear spin, but not as quickly. The big gear is actually going to turn slower than the little gear, and we're going to talk about the connection between that. That's actually going to be the constraint for the problem. So what you would do if you're working this problem is just like we've done on all the others. Do your diagram. Let's do the A frame first, and we're going to do, for both of them, A frame and B frame, we're going to do absolute angles. So XA, YA. First angle is theta 1. And by now, you've done your first homework, so I assume you're comfortable doing this now. XA, cos theta 1 xn, sine theta 1 yn, YA negative sine theta 1 xn, cos theta 1 yn. ZA is ZN. We're doing a simple rotation, right, around the shared Z axis. So what is this? This is our rotation from N to A. All right. Okay, so that would take care of the location description for A. We can, you can just write it up here. Here's our location description for A. So, P and A, R and A, right. We need to do the same thing for B frame, but how different is B frame going to be? You're going to do a diagram again, and it's not going to go from N to A. Now it's just going to go from N to B. And this isn't theta 1 anymore, now it's theta 2. And of course, you just go through this description and change all of these 1s to 2s. So 2, 2, 2, 2, and then when you call out the the rotation, of course, it's into B. There we go. So we have this. Now we can come in and we can declare location description of B, P and B, R and B. Okay. So the position orientation on this problem is honestly really simple, right? You've got two bodies, neither of them translate, they both rotate, and they have different angles, so boom, that's it. So let's clean this up now, and let's move on to the next step. Next step is going to be just listing the number of generalized coordinates. If you go through the position, you saw that we used fixed lengths using fixed directions, so there's no coordinates there. And then we had these two frames. We had the A frame and the B frame. A frame has theta 1, B frame has theta 2. So, how many generalized coordinates? We had two of them. What are they? Theta 1 and theta 2. That's it. Now, by intuition, how many degrees of freedom are in this problem? Well, remember, degree of freedom just means independent coordinates, right? So the coordinates are theta 1 and theta 2. If I were to reach out and grab gear B and spin it with my hand, I would be changing theta 2. And in so doing, because gear B is meshed with gear A, that's going to make gear A also move. So there's a connection between theta 2 and theta 1, right? Only one of those two can be independent. If you specify one, or if you change one, you're going to change the other one. So by intuition then, we can say that there's 1 degree of freedom. We know our equation. We need to take the number of generalized coordinates. We subtract the number of constraints, and we're going to get the number of degrees of freedom. So if there's 2 generalized coordinates and there's 1 degree of freedom, that means we have to write 1 constraint. And remember the rules for constraints. Scalar math equations that allow you to solve for a generalized coordinate. In this case, we're going to solve for one angle in terms of the other angle. Now, the constraint for gears is the gear ratio between the two, and there's actually 2 ways that you can write it. Pick one, and either one is acceptable. So the gear ratio is going to be RA theta 1. Now, this is the radius of A. So I'll just attach it here to the frame. We'll just draw it right there. That's fine. So there's the radius A, and then there is the radius of B, theta 2. So it's the radius of a gear with its respective angle, the radius of the other gear with its respective angle, and let's consider something. Suppose that I take gear A and I do a positive rotation on it, right? Like I grab this thing and I turn it. So what's going to happen? Drawing the 2 gears, and obviously I haven't drawn the teeth. But if gear A is doing a positive rotation, that means it's moving this way. And as it moves that way, it's going to push the teeth of gear B down, which is going to make gear B rotate this way. So they rotate in opposite directions. So that means the constraint has a negative on it. Yeah. So I said there's 2 ways to write the constraint. Here's the first way. The second way to write the constraint, I'm going to use a lowercase n. So n a theta 1. Now what this n is, this is the number of teeth on A. That's what I mean by NA, the number of teeth on it. So you've got a gear in front of you, and the gears have these teeth on them. And that teeth is, the number of teeth is obviously an integer. You're not going to have 0.7 of a tooth somewhere along it. So this will be an integer. It's the number of teeth on A, and then this is equal to the number of teeth on B, theta 2. And of course, we still have a negative sign on this one. One more comment about these radii. If we draw one of these gears with the teeth, then you can see that there's an inner radius and an outer radius. So which one do you use? Which one is this? It's actually neither. There is another radius in this region in between, and that's actually this radius we're talking about here. When you study gears in your later classes, you'll get to go through all these details. Now, for my class, it is perfectly acceptable for you to just write the radius or the number of teeth. That's fine. You might be looking at this and wondering what is the connection between these, because this seems almost convenient if this ratio of the radii is also the ratio of the number of teeth. And when I say ratio, here's what I mean. Let's take these equations and let's solve them. Let's say that the output is theta 2. So let's solve them for theta 2. So the first equation, this is going to become theta 2 equals, we're going to move the negative to the other side, RA divided by RB times theta 1. And we can do the same thing to the second equation. We can say that theta 2 equals negative NA over NB theta 1. So here's what I'm saying when I say the ratio. This is the gear ratio for this particular interface between these two gears. This ratio, the number of teeth, must also equal this ratio for the radii. The connection between these is actually the number of teeth per linear distance on the outside of the gear. And that number, however many teeth per distance, it actually has to be exactly the same for these two gears in order to properly mesh. If that number is not the same, when you attempt to put the gears together, the teeth are going to hit and they're not going to be able to mesh correctly. So either of these equations is acceptable for your constraint. I do not need or want both of them. So you pick which one you would like to use. Consider that they're both scalar constraint equations, right? And they allow you to solve for one of these variables in terms of the other. And when you're working these problems, you don't have to rearrange them. You could also just write them like these, and either one of these is fine as well. So I know I have 4 equations up here. You pick one, right? And that one is your constraint. So at the end of all of this, what do? You have listed the number of generalized coordinates. You have derived a constraint equation, and that means 2 generalized coordinates minus 1 constraint equals 1 degree of freedom. And that's it. That's it for the gears. So let's talk about pulley systems, and we can do that one very quickly. So what I'm going to do, I'm going to leave this diagram of the gears up, and we're just going to draw a pulley system right underneath it. And when I say pulley in this case, I'm not talking about ropes and cables. What I mean is we have 2 discs. So again, this is A and this is B. This time they're not meshed together with gear teeth. Now they have a belt. So this is a belt and pulley system. So a belt is wrapped around these 2. Now, just like gears, you will also study these types of belt pulley systems in your mechanical design class. There's all kinds of science that goes into the geometric shape of the belt, whether this belt itself has little teeth on it that fit into slots on the inside of these discs. There are those types of belts. What the belt is made out of, rubber reinforced with steel cabling, etc. But let's consider what's going to happen when disc A rotates. One thing we're going to assume about this belt is that there is no slipping. So when I say slip, imagine that the disc A was spinning and it was sliding against the belt. Well, if it's sliding against the belt, I mean, you could have an extreme case of slip where the belt is not moving at all, right? And this is just freely spinning, and there is complete slip between disc A and the belt. An analogy for that in a car is you could imagine being in a car and you're at a red light and the light turns green and you stomp on the gas, and let's say that the road is very slick, there's a lot of water on the road, and you're in a rear-wheel drive car and those wheels just start spinning, right? That would be slip. In this case, you can no longer connect the rotation of the wheel to the translation of the vehicle, which is what we want to do. We want to be able to connect these variables together. In this case, if we were slipping on the belt, we can no longer connect the rotation of disc A to the translation of the belt. So we are going to make the assumption that there is no slip. If there is slip, that complicates it a little bit, and we're not going to work those more complicated problems in this undergrad class. So we're going to say no slip. And imagine what happens, assuming no slip, imagine what happens when disc A is spinning. That means disc A is going to be turning and it's going to be feeding this belt in this direction, right? Positive spin, and it's going to feed the belt along with it. The belt is then going to make contact with disc B. There's going to be no slip at disc B, and then that's going to drive disc B. It's going to make disc B spin. So if A spins in this direction, it feeds the belt around, and that belt is going to make B spin actually in the same direction this time. So we saw in the gears that they will spin in opposite directions. With a belt and pulley system, they spin in the same direction. How different is the setup for position orientation? You need an inertial reference frame. You need some inertial reference point. These bodies do not move. These bodies both have their own frame. I'm just going to say A frame. There you go. And B frame. A frame is going to be a function of theta 1. B frame is going to be a function of theta 2, just like we saw in the gear. So the setup for the gear and pulley is actually exactly the same as the setup for the gear. The only difference now is the constraint equation. So in the belt and pulley system, we have two generalized coordinates. They are theta 1 and theta 2. So what's the constraint? Well, let's say that this is a smooth belt and there are no teeth. So now the only thing left to work with are the radii. So the constraint this time, RA theta 1 equals RB theta 2. And this time, because they are rotating in the same direction, it's a positive relationship between these. Okay, so two generalized coordinates, one constraint. This is the constraint. Here it is. Here's your pulley, your gear and pulley constraint. So now, two generalized coordinates minus the one constraint, and we're going to be left with 1 degree of freedom, which of course makes sense intuitively. If we turn this one, we're going to make this one spin. All right, so that's it for the dynamics for these problems. You're going to study these more in depth. You're going to learn all about how to design these teeth. You're going to learn all about selecting belts. Some interesting things with belts, there's usually tension in one side of it, and then the other side tends to have a little bit of slack in it, so the majority of the force is on one side of the disc. You will learn all about this, and you will have to consider this when you go to design those parts. But for now, this is what you need to know. So we're going to come back with some more videos later, and we're going to do all of the other constraints that we need to study. But that's it for this one. I will see you next time. Adios.